Okay, let's look at some examples of questions on the photoelectric effect. So what we're basing this on is the fact that you've got photons coming down, each with an energy of a certain amount, given by the frequency. There's a certain amount to get them out as a work, a certain amount of energy needed, and the energy left over will be transferred to the electron from one collision here, passes the energy onto one electron. Some of that energy is used to overcome the work to get out, and the rest of it goes as kinetic energy. And the maximum is based on the work function, the minimum energy to get it out. Okay? So the arrangement for that then, if you look at it, is the energy of the photon coming down, HF, needs to be equal to the energy electron that you're transferring it to. Okay? Electron energy. And when you look at that, it's using it to overcome the work function, and the rest of it's going as kinetic energy maximum. So you can rearrange this and get K max is equal to HF minus W. And there's a few iterations of that. If you know the stopping voltage, you can actually work out K max, because don't forget the K max is equal to the potential energy that the electron has got when it gets near that ring and you just drop the current to 0, and that's equal to delta VQ, the work done. So if you know the stopping voltage and the charge in an electron, you can work out the K max and vice versa. All right. Also be aware that if they give you a wavelength, you can use that formula to use for wavelength instead of that one. And also be aware that work is also equal to HF naught, the minimum energy based on the fundamental frequency needed to get any sort of electrons released from that. So let's just base it on this sort of stuff here when we do these questions. So let's try last year's. When the smoke particles enter the unit, they reflect the monochrome light from the LED onto the cell. So they're going to come down here, and the smoke particles will deflect it this way, and you get some sort of photons arriving at the photocell, and they're releasing electrons, giving you a current, and that's what sets off your fire alarm, I suppose. So the work function here is 1.55 electron volts. That's your work function, and that's the metal one, and you've been asked to work out the threshold frequency. Now in this case, you don't need this whole idea of K max equals HF minus W, because there's a very simple relationship between the work function needed to get out and the energy of the photon needed coming in. Okay? And that is W equals HF naught. So based on that issue, we'll do it in one go. So F naught should be W over H. So the energy of the photon needed divided by Planck's constant. So 1.55. Now you can't use that in electron volts. We need to get that into joules first. So convert it to joules by times by the charge of an electron, and then divide by Planck's constant. So you get 3.74 by 10 to the 14 hertz. Okay, so it's a pretty basic one. Let's go further down here. The number of smoke particles in the smoke alarm increases, so we're going to turn the number of smoke particles up. Use the concept of photons to explain the effect on the increased number of smoke particles on the electrons, or the energy of the electrons. So if you put more smoke particles through here, and there's more particles there, you get more deflection, so you should get more photons knocked off and reflected to this area here. So more electrons should be released based on that, so the intensity should go up. But will they be any higher in kinetic energy? And the answer is no. And the reason for that is that only one photon will hit any one electron, and the energy of this as a maximum is only dependent on each individual photon. So having more photons colliding with more electrons will give you more electrons, but each electron will have no greater energy. Okay? So what would you say is a key point here? So it's important to point out there's going to be more photons because there's going to be more deflections of photons from the increased number of particles. Also based on that, each photon only passes all of its energy to one electron. So if you check that, none of the electrons are going to come with any more energy because they're only going to get their energy from one photon, and that energy is not changing, only the number of photons coming down. So you could also point out here there's going to be more photons, and they're going to collide with more electrons and give you more of them. Okay? So the number's going to increase in terms of electrons, but they're not going to have any more energy. Okay. Okay, so what we've got here is an experiment being done for the photoelectric effect, where they measured the maximum kinetic energy based on incoming frequencies of light on a metal. So you've got different frequencies of light coming in. They've got some data points for each frequency versus the maximum kinetic energy of the electrons. And the first question was, what's the significance of part A, or position A, and position B? Well, position B here, it cuts that frequency axis there, is actually the threshold frequency. That's the minimum frequency you need to release electrons. Okay? For anything from there up, you'll get electrons being released. Now anything less than that, you'd actually have negative energy still for the electrons inside. In fact, the minimum energy to get any out would be here, and that's your work function, or minus your work function in this case. So that could have a value of, say, minus 4.0 by 10 to the minus 19 joules in that position there, and so the work function is 4 by 10 to the minus 19 joules. That's the minimum energy to actually get electrons out of there. Okay, so there's your one work function value and the F0 value. So it's interesting to note that if you try to draw a graph of this, all you need is the F0 value and the work function value. If you have those 2 points, draw a line through them, that will give you your trend line for a typical metal that you might be measuring. Okay. Now in this one we've got a photocell here, and it's got a sensitive ammeter attached to it. It's got a potential difference adjusted to give an ammeter reading of 0, so they're just going to turn that potential difference up, the stopping voltage or the stopping potential, until the current on the ammeter reads just 0. So you'll just stop the fastest ones. The work function is given here, so it's your W, and they've told you the photon energy there. They want you to work out the stopping voltage. So this is a situation where light's going to strike the photocell, overcome the work function, and release electrons of a certain energy there. So if we've got a basic on this one here, Kmax equals HF minus W. Now we don't need to use the HF here because we've been told the energy of the photons already. It's actually given to us as 8.62 by 10 to the minus 19 joules. And we've been told the work function in joules as well, so it's very nice of them to actually give it to us in joules. So this has all been given in joules. So you're just looking at the energy of the photons coming in minus the work to get it out, and that's going to be the kinetic energy of the electrons. So that's by 10 to the minus 19. So looking at those two there, if you do that, you're going to get 5.02 by 10 to the minus 19 joules. So that's the kinetic energy of electrons coming off here. Now, but that's asked me for the stopping voltage here. So some things to remember here is you could convert this into electron volts straight away by dividing by 1.6 by 10 to the minus 19. And if you know how many electron volts the kinetic energy is, the stopping voltage will be the same in volts. So in this case here, if we divide that through, we're going to get 3.14 electron volts. So that means that the potential difference needed would be 3.14 volts. So that's an energy, that's the amount of volts you need. The other way to look at this is that Kmax is equal to the work done on those electrons to stop them, which is delta VQ. We've got the work done, you're going to have to stop 5.02 by 10 to the minus 19 joules. And we're trying to find delta V, and the charge of an electron is 1.6 by 10 to the minus 19. So rearranging that, of course, you do end up dividing by 1.6 by 10 to the minus 19. But that'll tell you the stopping voltage anyway. You can also go the other way, and if someone tells you the stopping voltage, you can work out the kinetic energy of the electrons in joules and go backwards and maybe work out the work function of the metal if you know the light coming down. Okay? Here's another photoelectric effect question here. This time we've got a magnesium plate and we've got a light source going on, shining on that at a certain frequency, and again we're measuring what's going on here with the electrons. So we're looking at frequency of this much here for the light coming down. The electroscope shows that the electrons are emitted from the magnesium plates that are coming off of it. And they've told you the work function of magnesium, this work function here, is actually 3.66 electron volts. And they want to work out the maximum speed of the emitted electrons here, which is a bit different. So again, you can go through the situation of being Kmax is HF minus W. And we've been given the frequency of the light coming down. So work out the energy of the photon. We've got 6.63 by 10 minus 34. That'll tell us the energy of the photon coming down. Then we've got to subtract the work to get it out of there, this work function to get it out. Okay? And that's 3.66 electron volts. Now you have to be very careful here because this is going to give you the photon energy in joules, alright? Whereas this work has been given to you in electron volts. So either you convert this to electron volts or you convert this to joules. They're going to be the same unit. So typically we'll go to joules here. And this one here would be 1.326 by 10 to the 18 in joules. If we want to convert this from electron volts to joules, we need to times that by 1.6 by 10 to the minus 19 here. 5.856 by 10 to the minus 19. So therefore the maximum kinetic energy of these electrons is going to be 7.4 by 10 to the minus 19 joules. Okay? Now that's what the kinetic energy maximum is for the electrons coming off from that metal surface. What you've got to bear in mind then is that's actually equal to a half mv squared for the electrons. Alright? And if we want to find out the maximum speed, we're really going to substitute that formula in and rearrange for v. So you're really substituting v equals root 2k on m 7.4. And the mass of an electron is 9.11. And you end up with a speed of 1.27 by 10 to the 6 metres per second. Okay, thank you.